Okay, so we have said this before in the previous two lectures. So our final goal is to remove all this unwanted feature from a given grammar and obtain equivalent grammar. So far we have shown how to remove this useless symbol and epsilon production. So today we will define unit production and show how to remove these unit productions. So then all this tree will be complete. So now first of all, what is unit production? So a production of this form, A goes to B, and by our convention we use this to mean that they are just variables, right? They are single variables. So this B is not some combination of variables or combination of, it's just a single variable. So this sort of production rule, A goes to B, is called unit production. And why is this kind of unwanted? Because see, again, it's not really doing anything. It's just changing the name of the variable. So A goes to B, B goes to C, this sort of thing can happen. And that is just some extra thing which is not really as useful in doing this thing. So we can replace this thing. So the point is we can if we have, say, a chain of unit production, say A goes to A1, A1 goes to A2, finally this N goes to B. So then we can have this A going to B, just the single variable. So all we have accomplished is just changing the name of this variable from here to here. So then instead of this, we could have just, so finally, we will have to have some something other than a single variable here, right? Some combination of terminals and non-terminals. Maybe a single terminal, just some symbol a, small b. So if you have something like that, so instead of this long chain, you can just put this A going to whatever. So suppose this goes to something, some alpha. So we can put some A going to alpha. So this sort of thing we can do. But the question is, now I said that if I have a chain like this, okay, chain of unit production, then it obviously means that this A derives B. Now, is the converse true? Now, if A derives B, so one variable is just being transformed into another variable, can I say that it always happens via a chain of unit productions? See, here we require the thing that this grammar should be without epsilon production. So there should not be any epsilon production here, because otherwise we cannot guarantee this thing. You see, otherwise what can happen? Say this A may go to, say, some 2, 3, 4 variables, say here 2 variables, B, C. And then, okay, so this should be B. This should be B. This can go to B if I have, say, this epsilon production in my grammar, if I have this thing, okay. So if this thing is present, then I cannot guarantee that it passes through all this intermediate step where each step is unit production, okay. So and okay, so now let us give so we will call this a unit pair, this AB a unit pair, if this happens, that you can derive just this B from just this A, okay. So A can go to B. So if that happens, then we will call this unit pair. And if our grammar is without epsilon production, then we know that AB is unit pair if and only if there is a chain of unit productions going from A to B, okay. If and only if it is without epsilon production, okay. So how can we find all the unit pairs? Again, like all this epsilon production and generating and reachable thing, so you already have seen that 3 times. So the same thing here. So here it can happen in any number of steps. We just parameterize it using, say, case steps, where this k is less than equal to I. So in less than equal to I steps, suppose you can go to B from A. So let's call that, those kind of, let's take those kind of pairs, and that set we call, say, ui. Okay. So what is u0? That means this should be a 0 step process. So that means this can only be A, right? So you only have this AA sort of pair in u0. And then when can you have AB in ui? So that means you have exactly k many intermediate steps, k many unit productions. So that means so say from here you finally go to some C here, and then from C you go to B. So that means from A you can go to C in, say, less than equal to I minus 1 many steps, and then from C to B you go in 1 step, because this is a production. Okay. So if this is the case, then this AB pair will be in ui. So again, this gives you a recursive definition of this ui, and like again all those thing that we done before in the previous two lectures. So there will be some n such that this un contains all the unit pairs. Okay. And you see that the way we have done it. So once you have ui equal to ui plus 1, then for the rest of the thing, so all this ui plus 2 will be this, which is this, ui plus 3 will be this. So once we have this, so this is bound to be equal to this thing. So this is in fact this. So how do we find this thing? We start with u0, and from ui we keep finding this ui plus 1 using just a simple thing. And the moment we stop getting any new pair, we know that we have got all the pairs. Okay. Now what are the unit productions here, and what are the unit pairs here? So you see that here is a unit production. So SA and AB, so those are unit pairs, right? So because of this, anyway, SS, AA, BB, that is unit pair anyway, and so this is obviously true for all symbols. So I'm not saying that. So other than that, we have SA. Because of this, we have AB. But since we have SA and AB, so that means A can go to A and A can go to B. So that means we also have SB. So this is also a unit pair, right? So what we can do here is, so our goal is to remove this unit productions, right? Now that means whatever this unit production is doing in this grammar, we should have some equivalent thing here which can do the same thing. Which can which enables us to carry out the same equivalent derivation for the same end product. So that means, so S can go to A, and then this A will have to expand into something, right? This A can just stay A because ultimately we are talking about the language, right? We want to keep the language intact, and without changing the language, we are trying to change this production. So we are trying to remove this unit productions. So so if we are deriving anything from S, so and if we use this production, then this A has to expand into something, and that something is either this thing or this thing according to this production rules, right? So instead of going to this two-step process, that this goes to this and then this goes to this, we can directly say that S goes to this or this. Okay, you see that we can combine these two things and say that S directly goes to this and this. Okay, we also have all the other S production. So this was here in this CFG, so we add that. So all the non-unit productions that we have here, we also have that here. So we are keeping all the non-unit productions, but for all the unit productions, okay, so so we are adding this thing. And here again, so what we can do, so now you see, this tells us what? So now we have discovered that SB is also a unit pair. So S can be just changed into B, right? And that's because just this this goes to this goes to this, right? And then B can be either of these two things. So instead of this three-step process that S goes to A goes to B, and then B goes to these two things, okay, so just to remove the requirement of using this production, so we do not want to use this production, and this production will be required in a derivation like this. So S goes to A goes to B, and then something like this. So S can go to this and this via this production. So we remove this thing and directly put this thing here. So S goes to either this or this. Okay. So we can also we will have to, so yeah, so this is not actually complete. So we will also have to use a production for, we will also have to use a production for A, some additional production for A. Why? Because A can go to B, and then B can go to either of these two things, right? So we will also have to add this production. So this A goes to these two things, this B, BB, and then this B. Okay. So I should have put it here, but anyway, so now this thing is equivalent with this thing, right? So what are we doing exactly? So if you see what we did here, we kept all the non-unit productions, and if we have a unit pair A1, A2 in G, and if A2 is going into something which is not just a single variable, some alpha which is either a single terminal or a combination of more than one terminals and non-terminals. So, but all that we need is, this is not just a single variable. So if that is the case, then we know that in this part we only have this unit productions. Okay, so we do not include these unit productions. Rather we just directly add this production in our new grammar, which is G prime. Okay, so this happens in G, so we do not include any unit productions that is involved here. Rather we include this. Okay, and you see that this is also included because of this property. So we are keeping all the non-unit production. This is a non-unit production in G, so this production is also in G prime by this rule. But if we have a chain of unit production here, and then if we have here, then we are also adding this additional production in G prime. So, and in this way this G prime will not contain any unit production, and it will be equivalent because it's generating the same language. So again, we have to have a formal proof, and we saw that we need this grammar from which we are starting to be epsilon and without epsilon production. So here is our theorem that let be this CFL without which doesn't contain epsilon, and it doesn't contain epsilon production. Why do we have this thing? Because as we explained this when we explained about removing epsilon production. So if you do not have any epsilon production, then you cannot have epsilon in your L, right? So this is required. Otherwise, you cannot have this part, that CFG, without epsilon production. Okay, so this does not contain epsilon and it does not have any unit production, such that this is accepted by this G. So then there exists another equivalent, this G prime. I'm accepting the same language, okay, such that this G prime does not have any unit production, epsilon production or unit production, right? So to begin with, we did not have any unit production. We are not introducing any new unit production, so that means whatever we are getting here, so it does not have any unit epsilon production, so that is fine. And also we are removing all this unit production, so this may have unit production, but this does not have unit production, right? And how are we removing this thing? We explained the previous thing. So if we have the production rules here as P prime and here we have P, so we add all the non-unit production here in P to P prime here, right? And if we have this thing, that this unit pair AB in G, and since this is without epsilon production, this means that this consists of just a chain of unit productions in G. And if we have this production in P, where again, so this alpha is not just alpha is not just a single variable, okay, in P. So then we add this thing directly. So this A is going to alpha, so we add this production directly into P prime, and we do not have any of the unit productions that are involved here. So in this way, this is so how to prove this? So we will again use this sort of thing. So we need to prove that if you can derive something in G prime, then you can also derive the same thing in G, and vice versa. So if you can derive that in G, you can derive that in G prime. And so to ensure this thing, we could have just done S here, but we can prove the stronger thing. So not just S, it happens for all variable X. Okay, in fact, this can be a terminal also, then this will be 0. So, and that is exactly the basis here. So this K is 0, that means this X is terminal, because this part is W. So I should have written for all W over terminals. Okay, this W is over terminals. So basis is K equal to 0, so this has to be a single terminal, and it just, so both this X is a single terminal, this is a single terminal, and this is 0. So that is the basis. And then if we have say this, and this is not 0, that means the first step is some production in G prime, right? And then this thing expands into some W1 up to Wn, where each of this Wi corresponds to so this is expanded from this Xi here, right, in Ki many steps, where this Ki is at most K minus 1, because this is just a sub step here. So that means this Ki is less than or equal to this. So when you are doing this, you can always assume that you are doing a leftmost derivation, just to be more clear. So you can have, you just assume that this is this thing is a leftmost derivation. Leftmost derivation. So by induction hypothesis, what do we have? So we have that this thing also is true for G, right? Yeah, so by induction hypothesis we have this from here, right? And you see that this is a non-unit production in P prime. Here again there is a typo. We should not have this non-unit production in both this and this. Yeah, all we can say that is a in P prime. Okay. Yeah, so this is a single step process in G prime, so this is a production in P prime. But then that means that we can derive this thing in G in multiple steps. Why is it so? Because this x going to x1 up to xn is in P prime. Why is it in P prime? You see, our rule was to add all the non-unit productions of P to P prime. So either, so that this means that either this was added to P prime because of this rule. So that means this is whatever this thing is also in P. Or why was it added? Because of this thing. So that means so this alpha here is this part, right? And this x here is this a part. So that means this was added to P prime because we had this thing. So this we had a chain of unit production which goes to some variable, and then this variable goes to this alpha. So that means there must be some, say, x goes to some y, say, using a chain of unit production here, and then this goes in just one step to this thing. So either this or this thing, where this happens in G, right? So this is G. So yeah, so in this case also you see that I can club this thing, this part with this, using just this star. So that means this x derives this thing in multiple steps, and then from here you again, this should not be a G prime, so this should be a G. Okay. So in G we have this thing because of this, right? So just correct this typographical error. So this is a unit production in just P prime. We do not have it in P, and then this should be star, and this is G. And the rationale for this part is this, that if this is in P prime, then either this is a production in P, or in G we have a multiple unit production here, and then we have this thing here. So again we can derive this in G totally. So this part is done. And the second thing is, if we can do that in G, then we can do this in G prime. So again that is easy. So we can do this in G if, say, what can happen? We can have some unit productions, some chain of unit productions at the beginning. So this can be 0 also. That means we do not have any unit production here. That is also fine. But we have 0 or more unit productions at the beginning, and then it expands into some more variables or non-terminals. So this part is non-unit production in G. Okay. So this thing, that x prime goes to this x1 up to xn. So this is a non-unit production in P, and so that means this is also a non-unit production in P prime. So this is both a non-unit production in P and P prime. And what else do we have? So in G we have that each of this xi is going to this wi using some number of steps which is less than k, right? because we have already used this j many steps here. Here we have yeah, this k minus 1 minus j, because one step is taken here. So all these things is less than k, obviously. Okay. So yeah, this is less than k, and as I said, this is a non-unit production in P, and you see that this, again, there should be a star here. So this is also happening in this G. So that means we have this thing as a non-unit production in P prime. Okay. So by this rule, if we have a star here going from A to B, and from B we go to alpha in G, so then we have a direct production from A to alpha in P prime. So here this instead of A we have X, and instead of this B we have this X prime, and instead of this alpha we have this combination. So that means this is a non-unit production in P prime. Okay. So by induction hypothesis, okay, so from here by induction hypothesis we have that this also happens in G prime. So this xi derives wi in G prime, and then we can club everything together, right? So this is production in P prime, so we can in one step have this in G prime. So we do not need this j plus one step here. This can be clubbed together in just one step in G prime, and then from here we can have the same things for each of this xi's in G prime. So we can finally derive this thing. Okay. So yeah, this is done. Now you see that when we are removing this epsilon production, unit production, useless symbols, we have to follow certain orders. Okay, because this unit production required that the grammar should be free of epsilon production. So first we need to remove this epsilon productions, and then we need to remove this unit productions, and then we can remove this useless symbols. And we should notice that while removing these unit productions, we did not introduce any new epsilon production, right? So that is why we have this theorem, that here we started with something without epsilon production, and here we also got something which does not have unit production, because here we are not introducing any unit here we are not introducing any epsilon production. We started something without epsilon production, and we got something without epsilon production. So that is maintained here, but we got rid of the unit production. So from here to here, when we come here, we do not have epsilon productions, and also we do not have unit productions at this stage. Okay, and as we said, when we are removing epsilon productions, the language we get is this given language minus this thing, right? So if it has epsilon, then you get this minus this thing. And then from here, so you, after removing this, you get this G1, and from G1 you remove unit production, you get G2. And in all these stages, the language is equivalent. So from here to here, so this L of G2 is equal to L of G1, right? So which is this thing. And then we arrived at this stage, and when removing useless symbol, again, if you see the proofs, okay, so all those proofs that we did not introduce any epsilon production, and we did not introduce any unit production while transforming the grammar from something to something, so by removing these useless symbols. So here we again use this two-step process by first removing the non-generating symbols and then removing the non-reachable symbols. But whatever we did not introduce any epsilon production or any unit production. So after doing all three steps in this order, we are left with grammar, say G3, where the language is same as this thing minus epsilon. If it has epsilon, so then just this minor discrepancy. So this is the big theorem that we have, that if L is a CFL, so that means if there exists any CFG for L, so then if we take this L minus epsilon, and if it is non-empty, why we require this to be non-empty? Because at this step, so if you go back to that useless symbol video, so while removing the useless symbols, we required the language to be non-empty, because if the language is empty, then S itself is useless symbol and we cannot remove S, because we have to have some start symbol. So yeah, so this means that so what is this language? This language is just this thing. So this thing is not empty. So if this is the case, then we can have grammar such that sorry, again there is a mistake there. This should be such that L of G is L minus epsilon. We can have this, where this G does not contain any useless symbol, does not contain any epsilon production, does not contain any unit production. Okay, so we have removed all this unwanted feature from this. And if our L contains epsilon, okay, so what we can do is we can take this part and first calculate all the productions which does not have any of this thing, and then just to introduce this thing, we can just introduce this production. So this kind of is quarantined into this one separate production. All the other production are quite nice, and we have like this. Okay. So, but generally we avoid language containing epsilon. So we normally talk about language without epsilon, precisely of this reason, that we can have a grammar which does not have epsilon production, and also which does not have useless symbol or unit production. Okay. So now suppose you have a grammar which does not have useless symbol. Not only can we say that it does not have unit production or epsilon production, we can further modify the grammar to transform the productions into this form. See, this is, so I am saying that given any CFL without epsilon, so any context free language without epsilon, so we had a grammar which did not have useless symbol or epsilon production or unit production. So here I am saying that we can have a grammar, so it is generated by a grammar such that it has no useless symbol, and the productions are of this form. So A either goes to BC or A goes to A. So that means this symbol goes to just a combination of two variables. So these are variables, none of these are terminals. So either a single variable goes to just two variables, or a single variable goes to a single terminal. Again, this is just a single terminal. Okay, so A, B, C are variables and A is terminal. Okay, and this is again very easy to do, because you see we can already transform our grammar so that it does not contain useless symbol, it does not contain epsilon production, and it does not contain say unit production. So let's start with that form. So let's first perform all these steps. Okay, and then suppose we have a production of this form. Okay, So that means which does not conform to this, which contains, so anyway it cannot contain something like A goes to B, right? Because it is free of unit production, because we have already done this thing. So this sort of things are not there. So only thing that is there is some A going to either a single terminal, say A, or A is going to a combination of something here, which has either two terminals or more than two non-terminals, something like this. Now if we have a production like this, we can break it down into productions like this, so where this contains only two symbols. So A goes to A D1, where this D1 captures this entire part. So D1 should go to this thing, but again we break it down. So D1, so this entire thing is, say, D1, and then this part, so from C to this, say, D2, and then this EF part, so this EF part is D3. So this D3 is EF, so then this D2 is just C D3, and then this D1 is just B, and then this D2, and then this A is just small a and D1. Now here we need both of these things to be variables, but that is also easily fixed, because now we can have productions like this. So here we have terminals what, A and C. So we introduce new variables just to replace, just for this terminals. So these are variables new, so these are new variables which goes to, this goes to A, this goes to C, and here in place of A and C we just replace it by CA and CC. Okay. So what are we doing? So first of all, to prove this theorem, we take any grammar, we take any context-free language without epsilon, and first we do this things, so that we know that our productions are either of this form, or it's either or it is of this form. So then we first introduce this new symbols for all terminals. For all terminals A, we use this sort of thing. Okay, and then this A can be broken into this thing. So this we first take the first symbol, so x1 and then something, so that remaining part after this thing is D1. So we can have x1 D1, but not exactly x1, because if this is a terminal, so if this xi is a terminal, so then this y1, so if x1 is a terminal, then this y1 should be something like this. So yeah, this, if this xi is a terminal, then this y1 should be C of A, right? Like here. So we did this. And if it is not a terminal, so then it is just this x. So if x1 is, say, x1 is a variable, so then we put x1 here, and remaining things we say that this is D, and again we break this D into either this x2 or something like this, some CA something, and the rest of the thing is D2. So just like this thing. So we can do that for arbitrary productions. So in this way we can break this thing into a series of productions which is of this form. Okay, and a grammar of this form which does not have useless symbol and all the productions are either of this or this form, this is called a Chomsky normal form. So you remember the Chomsky hierarchy for languages and all, so it's the same. Noam Chomsky is still alive. So this is the Chomsky normal form for a grammar. So it says that for any context-free language, you take any grammar accepting that language, and then you can transform that grammar into this form, into this normal form. This is called Chomsky normal form.